Molasses. So the purpose of this lab was to explore the effects of Faraday's law and Lenz's law through real experimentation with a falling bar magnet and a tube of aluminum foil. The interactions between these two objects led us to see a non-Coulomb electric field and induced EMF due to changing magnetic flux, and this non-Coulomb electric field produced an induced current which aimed to counteract the change in the original magnetic field. Some of the fundamental principles explored throughout this lab are Ohm's law, relating I equals to VR, Faraday's law, or how the change in magnetic flux over time induces a non-Coulomb electric field, which thus generates an EMF, and Lenz's law, or how a B field is always going to be induced in an opposite direction of a changing magnetic field. Furthermore, we're going to explore Biot-Savart law for dipoles because we are using a magnetic bar. And a brief result of our final results is the fall time with the aluminum foil was 1.41 seconds, and the calculated fall time was 2.699 seconds. So the initial conditions for our experiment was that enough aluminum foil would be present and that the magnetic north would be pointed in the upwards direction. The system is going to be our nickel magnet in the aluminum foil tube. Our surroundings are going to be everything else, so gravity due to Earth, external electric devices, etc. The procedure involved utilizing a roll of aluminum foil with a cardboard tube in the center, marking the north pole of the magnet, and then dropping it through the center of the tube 5 times. Then you're going to want to record the time it takes from when the magnet enters the tube to when it leaves on average. Some of the assumptions are that the air resistance is going to be negligible, and the only force components acting on the magnet are the aluminum foil and force due to gravity. So in our experiment, the average drop time was about 1.41 seconds. The full foil tube dimensions were 0.42 meters for length, 0.039 meters for diameter, 0.028 meters for inner radius, and the foil thickness was calculated to be 1.1 centimeters, satisfying our initial conditions. So in the computational model, some of the initial conditions were that we needed to initialize the geometry of the tube from the previous slide, as you can see here. And then we needed to also define the magnetic field equation for a dipole using the equation I discussed earlier here. Next, we needed to calculate the change in flux over the change in time, which I did in this section of code. And then we also needed to initialize the force due to gravity using only in the y direction. Finally, we needed to employ Lenz's law to make sure that the induced current would be opposite of the changing magnetic flux. And we needed the angle perpendicular to mu hat and b hat in order to calculate the magnetic field at each ring. Finally, the computational model results, as you can see in the graph to my left, the actual dropping time was 1.41 seconds. The computed dropping time was 2.699 seconds. Some of the observations are that the blue color on the bar means the current is going to be clockwise and our induced current is negative. Flipping the magnet would result in an opposite magnetic field because the induced current would be flipped, and the differences due to the computational model omitting things such as friction and air resistance. If, as you can see here, as the velocity is decreasing, the magnet is decelerating due to the net drag of the magnetic field, and as the velocity increases, the magnet accelerates due to the net force being applied to the magnet. And finally, during times when there's a constant velocity, the force due to gravity is assumed equal to the magnetic force. So some of the discussion questions: what if the resistivity of the conductor were reduced as close as possible to 0? How would the dynamics of the falling magnet change? The current increases as resistivity decreases due to Ohm's law, I equals V over R, so as a result, the magnetic field would be stronger within the tube. Similarly, effect on velocity of the magnet would decrease. For example, the magnet would fall more slowly. So what if holes or slots were cut into the tube? How would this affect the ring currents in your model? The area of the conductor would decrease, and as a result, the change in magnetic flux across the tube would decrease, as can be seen by Faraday's law equation right here. So the current might fall faster in areas with holes or slots due to the absence or erratic behavior of a magnetic field. So some of the errors are that human error for time measurements on the fall duration of the magnet, the length of the tube, or the diameter and width of the foil, and the fact that there's A non-uniform magnetic field throughout the tube could be apparent because aluminum foil thickness may differ throughout the length of the tube. Some differences between the computational model and our experiment was the computational model didn't take into account friction of the magnet against the aluminum foil tube. It also didn't take into account air resistance. And finally, the computational model is using an arbitrary magnetic dipole moment mu from a previous lab, which may not be the actual dipole moment in real life. Thank you.